welcome to the next module. In this module, what I would like to spend some time on is related to elementary graph algorithms. The last module, we saw structural coverage criteria related to graphs. We saw how to define test requirements for various structural coverage criteria. We began with node coverage, edge coverage, went on till we saw prime path coverage. The next thing that I would like to focus on as far as testing is concerned is how to define algorithms that will help us to write test requirements and test paths that will achieve various graph coverage criteria. It so turns out that the algorithms that will help us to write test paths and test requirements for graph coverage criteria use elementary graph search algorithms. Most of them use, in fact, BFS, breadth first search. Some of them can also use things like finding strongly connected components, finding connected components, etc. So once you know these algorithms very well, it's a breeze to be able to work with algorithms that deal with structural coverage criteria on graphs. So what I would like to spend time on in this module and in the next module is to help you to revise elementary graph search algorithms. We will look at breadth first search in this module. In the next module, we'll recap depth first search and also look at algorithms based on DFS that will help us to output strongly connected components. Once you know these algorithms, we'll move on, come back and look at the algorithms to write test requirements and test paths for structural coverage criteria based on BFS and DFS, right? Let's begin at looking at what are the standard representations of graphs that algorithms that manipulate graphs will look like. Right? Graphs can be represented in two standard ways, as you might know, as an adjacency list and as an adjacency matrix. Right? Both undirected and directed graphs can be represented both as an adjacency list and as an adjacency matrix. It so turns out that in testing, when we look at graphs as data structures modeling various software artifacts, we will never look at undirected graphs. They're not very useful to us, maybe except rarely when we look at, uh, let's say, class graph or things like that. Otherwise, most of the graphs that we will deal with will be directed graphs. But why I'm saying this is that the algorithms that we will look at in this module and next module work both well for directed graphs and for undirected graphs. We will use them for directed graphs. So we'll go ahead and see what an adjacency list looks like. So given a graph with vertex set V and edge set E, what is an adjacency list? An adjacency list keeps an array of lists. How many lists are there in the array? There is one list for every vertex. So totally there are mod V lists. What do each of these lists contain? Each of these lists contain all the vertices that are adjacent to the given vertex V. That is, it contains each vertex U such that UV is an edge in G in the graph. Right? So what does an adjacency list contain? It contains an array of mod V lists, one list for every vertex, where the list for every vertex contains all the other vertices that are connected to this vertex through an edge. Right? What is the size of an adjacency list? If you see for directed graphs, the direction of the edge don't matter, right? So when I have an edge UV, I practically have two edges, UV and VU. So for undirected graphs, the size of the adjacency list is 2 times mod E. One edge, two edges for every edge present in the graph in the adjacency list. And for directed graphs, there is one, for every edge, there is one vertex somewhere in the adjacency list of some vertex. So the size of the adjacency list is mod E, right? So for both directed and undirected graphs, the total size of the adjacency list will be this. This first mod V in the theta component represents the number of lists, and each list can be at most mod E size, right? So the total size is theta of mod V plus mod E. Moving on, what does an adjacency matrix representation of a graph look like? Adjacency matrix of a graph is a mod V by mod V matrix. So it has as many entries as that of the number of vertices. It's a square matrix and it's filled with 0 and 1 entries. It contains a 1 at vertex VIVJ if the edge VIVJ is in the set of edges of the graph. Otherwise, it contains a 0, right? So if you see adjacency matrix of both directed and undirected graphs will need v squared, theta v squared memory because they are of matrices of size mod v by mod v. In addition, for undirected graph, because the edges are there on both sides, the adjacent transpose of its adjacency matrix will be the same as the given adjacency matrix. So, which is good for what kind of graphs? Graphs could be dense or they could be sparse, right? So, if a graph is sparse, means it has very few edges. It has lot of vertices. It has very few edges. Trees are examples of graphs that are sparse. So, if graphs are sparse, then adjacency list is considered to be a good representation because the size of each list for every vertex will be small. On the other hand, if a graph is dense, which means it has a lot of edges, the number of edges is close to mod v squared, then an adjacency matrix is considered good because the size of the adjacency matrix is fixed to be v by v matrix. So if there are many edges, it just means more 1 entries, lesser 0 entries. Whereas if it's an adjacency list for a dense graph, then the size of each list would be really long. So for sparse graphs, adjacency lists are considered to be good. For dense graph, adjacency matrices are considered to be good. Otherwise, there is no really big trade-off about one representation or the other. It's just for the convenience of our this thing. In our algorithms, we will mainly use adjacency lists. The algorithms that we will deal with in these two modules, we will use adjacency lists. Right. So, what are the elementary graph search algorithms that we will be looking at? We look at three algorithms because these three are the main ones that we will need for test case generation. So, we look at breadth first search, which we will do in this module. The next module, I'll help you recap depth first search, and we'll also depth first search and breadth first search have several applications. So, we look at one particular algorithm which deals with how to compute strongly connected components or connected components using depth first search. So those two we'll look at it in the next lecture. So we'll move on and start with breadth first search. What does breadth first search do? As the name says, it searches through a graph. And how does it search through a graph? It searches through a graph in a breadth first way. That is, it starts its search from a particular vertex. Let's say call it the source vertex. And what it does is that it first explores the adjacency list of the source vertex. That is, it explores the span of the breadth of the graph at the vertex x. Once it's finished exploring the adjacency list of the vertex S, which is the source, what does it mean to explore? It adds it to a particular queue that it keeps. It goes ahead, takes one vertex at a time, and explores that vertex adjacency list, and it goes on like this. So, this way of searching or traversing through a graph by exploring the adjacency list of each vertex fully is called breadth first search because it explores the graph in a breadth first way. It doesn't go deep, unlike depth first search. As it explores, it also computes a few things which are useful for us to keep, right? What it says is that as it explores, it also keeps track of, given a fixed source S, what is the distance of any other vertex in the graph from the source S. We look at graphs that don't have any attributes like weights and other things attached to its edges. So for us, distance plainly means the number of edges. So how far is a particular vertex in the graph from the designated source vertex? How far mean how many edges are there between the particular vertex in the graph that is reachable from the source vertex. That is what is called the distance of a vertex from its source. Breadth first search also computes the distance. It so happens breadth first search computes the smallest distance or the shortest distance. We'll see what that is in a little while. And it once you explore a graph by using breadth first search, and the result of that exploration is a tree containing the path from the source to all other vertices that are reachable from the source. Such a tree is called the breadth first tree. Breadth first search algorithm can be used to output the shortest distance of every vertex from the source. It can also be used to output the breadth first tree which contains the shortest path from the source to every other vertex, right? So here is how the algorithm looks like. Before I show you the pseudocode of the algorithm, I will tell you what it does, right? So it takes the graph, and the main job that breadth first search does is to be able to color each vertex in the graph, right? It keeps a queue of vertices, and that queue contains a queue of vertices that are colored gray, right? So what does breadth first search do? It color codes every vertex, and there are three kinds of colors that it keeps. To start with, every vertex is colored white, right? And then a vertex that is colored white further changes to colored gray, and after it's colored gray, it changes to color black. Once it changes to color black, we say we are done with exploring that vertex fully, right? So to start with, all vertices are white, and when does a white vertex become gray? It becomes gray when it enters. So breadth first search maintains a queue of vertices, and when it enters this queue, it becomes gray. So it becomes gray when it's first discovered as a part of an adjacency list of some vertex, and then it's put into the queue, right? When it's put into the queue, the aim is that it's gray colored, it is discovered now, but I am yet to explore this vertices adjacency list, right? So I put it in the queue to remember that I have to do that, and I move on and explore the adjacency list of all other siblings of this particular vertex. And then when I come back and explore this particular vertices adjacency list, I finish exploring that, then I color it black. And when I color it black, I remove it from the queue, right? So how does the breadth first search work? So here is what is the pseudocode for breadth first search. So for each vertex that is not the source, remember S is the source from which breadth first search algorithm starts. So for each vertex, read G dot V as for each vertex in the graph that is not the source, which is not S. Set its color. So we keep three attributes with each vertex. We keep a color attribute, which tells you what the color of the vertex is. It could be white, gray, or black. We keep a D attribute, D for distance, which tells you what is the distance in terms of the number of edges of this vertex from the source vertex S, right? And we keep a pi attribute, pi representing predecessor or parent, which tells you who is the parent of a particular vertex in the breadth first tree that this algorithm is going to output. So what are the three attributes that we keep with every vertex? A color attribute, a distance attribute which tells its distance in terms of the number of edges from the source, and a predecessor or a pi attribute which tells you who is the predecessor of this particular vertex in the breadth first tree. So to start with, breadth first search algorithm colors each vertex Y, sets its distance to be infinity, because the distance will reduce, right? To start with, I don't know how far it is from the source, and the tree is not yet developed, so the breadth first search algorithm is just begun, so its pi attribute is nil, right? Now it begins its search from the source vertex S. So the first thing that gets into the queue, Q is the queue that it maintains. The first vertex that gets into the queue is S. So if you see this NQQS, puts S inside the Q. So when it puts inside the SQ, the color of the vertex S is gray. S, the distance of S from itself is 0. S is its own parent, so it doesn't have any predecessor. Its predecessor is set to nil. So Q is initialized and S is put into the queue. So as long as there are vertices in the queue, which means as long as there are gray colored vertices, what do? You pick up the first vertex available from the queue, you dequeue it, right? And you start exploring its adjacency list. That's what this one for loop on line number 8 does. So it says for each other vertex in the adjacency list of the vertex U in the graph, if its color is white, then you make it gray, which means you have discovered that vertex now. You set its distance from the source S to be whatever the distance from the source S of U was plus 1. And then you say its parent in the breadth first search tree is going to be U, because I found it as a part of the adjacency list of U, so it's natural that its parent is U. Right? Once you do this, you add V to the queue that you maintain. And you keep doing this till you finish exploring the adjacency list of U. Once you've fully finished exploring the adjacency list of U, you come out and color U as black. Right? So is it clear what the algorithm does? Just to quickly repeat, to start with, it colors each vertex white, sets the distance and pi attributes. It begins its search at the source vertex S, adds S to the queue, colors it gray, sets its D and pi attributes. And then for each vertex in the queue, it takes it out from the queue, explores the adjacency list of the vertex that was just taken out fully. What does it mean to explore the adjacency list of the vertex? It looks at each vertex in the adjacency list of the vertex U. If it was colored white, which means it was not yet discovered, it says I am discovering it now, marks it gray, sets its distance from S as the distance of U from S, which was already set, plus 1, sets its parent in the breadth first search tree to be U, and adds it to the queue. When it's finished doing this for all of the adjacency list of U, it removes U from the queue here and colors it black, right? So here is an illustration of how breadth first search works on a small example. In this particular case, I have taken an undirected graph as an example, but as I told you in the beginning, directed or undirected graph doesn't matter. The algorithm will work fine because it just takes an adjacency list as input and doesn't really worry itself about whether the graph is directed or undirected. So there are 8 vertices in the graph. The vertex S is the source vertex. So what are these various things? So the other vertices are R, S, T, U, V, W, X, Y. So I have also put these parameters inside the vertex. What they correspond to is the D attribute. So if you see, the distance from S, the source, to itself is 0. To start with, every other vertex has distance infinity from the source S. The Q initially has S, its distance to itself from itself is 0. Now I start exploring the adjacency list of S because that's what is there in my Q, right? So what are the 2 vertices that are adjacent to S? That is R and W. So this blue colored arrow, I hope you can see them, means that I have set the predecessor attribute. So I have set the predecessor of R as S and I have set the predecessor of W also as S. So far my breadth first tree that I output, which I read out from the predecessor attributes, contains this subgraph. It contains the node S with its successor as R and another successor as W. And because I have discovered these 2 vertices for the first time, I put them in the queue and set their distances from the set S to be 1 because they are just reachable from S through one edge. Now I can put them in any order. It just so happens in this case that I put W first and then R. Nothing will go wrong in the algorithm if you put R first and then W. Now, because I have put W first, I start exploring the adjacency list of W. What are the 2 vertices that are adjacent to W? If you look at the third figure here, T and X. So I add them to the breadth first tree, which is again setting its pi attributes. So I color this as blue, indicating that the predecessor of T is W, and then I color this edge also blue, indicating that the predecessor of X is also W, and I add T and X to the queue. And how far are they from the sources? They are at distance 2 from the sources, right? Because there are 2 edges. Takes 2 edges to reach T. Please remember that I have not colored vertices gray in this example because it became a little cumbersome to do it. But all the vertices that are there in the queue are all colored gray, but it's not depicted in the figure here. I move on like this. Now I start exploring the adjacency list of vertex R because that's what is there at the head of the queue. So V is adjacent to R. So I add V to the queue here, color R black, and come out. Now the next element whose adjacency list needs to be explored is that of T. So I take T. There are 2 vertices adjacent to T, that is U and W. W has already been explored, it's colored black, so no need to explore it once again. So I add U to the queue, set its distance from S to be 3, and color T black. And I go on like this. The next vertex to be explored is X. So if I take X, the only other vertex, unexplored vertex that is incident to X is that of Y. The remaining 2 vertices T and W are already colored black. So I add Y to the queue, set its distance attribute to be 3, and color X black. I move on like this and keep adding till I can. At some point, the queue will start shrinking and the queue will become empty. So when will the queue become empty? When I have finished all the vertices and colored all of them black. So if you look at this final tree, how to read this tree, it says S is the source, and you just read out the blue arrow edges as the tree. So the tree has an edge from S to R, and the tree goes like this: S to W, W to T, W to X, X to Y, T to U. So breadth first search as an algorithm outputs this tree by saying that I have explored all the vertices, and it also outputs the distance of each vertex from the tree, right? So I hope the algorithm is clear to you. So what do I do to start with? I take a graph. I start from the source. I explore the adjacency list of each graph. That is what it means to say that I go in a breadth first way. And I keep doing till I finish exploring. And the output of breadth first search is basically a tree that I read out from the pi or the predecessor attributes, and the distance of each vertex as it occurs in the tree from the source S. So, what is the running time of breadth first search? If you go back and see the pseudo code of breadth first search, so there is this initial for loop that runs once for each vertex. So, this takes order big O of v time. And then this while loop, right, runs once it enqueues a vertex, it doesn't really go and put it back again. Once it enqueues and dequeues it, each vertex gets in and gets out of the queue exactly once. And for each vertex, it explores a for loop along the length of the adjacency list of that vertex, right? So BFS scans each adjacency list at most once, and so the sum of the lengths of adjacency lists, as we saw, is theta e. And I told you the initial for loop takes big O of v, so the total running time of BFS is big O of v plus e. So it's a linear time algorithm that is linear in the size of the graph. So when I talk about the size of the graph, we typically consider the vertices and the edges, the number of vertices and the number of edges. We don't really say only the vertices. It's a wrong thing to say. You have to include the size of the edges also as very much a part of the graph. So BFS runs in time linear in the size of the graph, right? So I told you along with breadth first search, it also outputs a few other things that will be useful. It outputs what is called the shortest path distance, right, from the source S. So BFS is run from a fixed source, and the shortest path distance is the distance in the BFS tree in terms of the number of edges. It so happens that BFS outputs the shortest path distance of each vertex from the source. Standard terminology that a book like a book called Introduction to Algorithms by Corman, Lysason, CLRS, Corman, Lysason, Rivest, and Stein outputs is the shortest path distance, and the notation that is used for this is delta. I've taken the pseudocode, these examples all from that book. It's a pretty standard book. So it outputs the shortest path distance written as delta from the source S to each vertex V, which is the shortest path in terms of the number of edges that it encountered. There are several properties that you need to show that actually BFS is correct. What does it mean to say BFS is correct? So we will state and prove a theorem like this. Let's read out this theorem. It says, suppose breadth first search is run on a particular graph from a fixed source S. Then, during its execution, BFS manages to find or discover every vertex that is reachable from S in the given graph G. And when it terminates, it outputs the shortest path distance from S to each vertex in the graph, right? For each vertex that is reachable from S, one of the shortest paths will be the path that the breadth first tree takes, right? So for vertices that are not reachable from S, this particular example graph that we saw didn't have anything like that. For vertices that are not reachable from S, breadth first search will not be able to output anything because it won't explore it. So what you basically do is you begin breadth first search from a fresh source that is not S. Then you can explore the graph once again from another source and reach all the vertices that were not reachable from the source S. And you can repeat this process to get a forest of breadth first trees till we complete. The way I have presented the pseudocode, it is presented in such a way that we present it as we are exploring from a fixed source S and then we stop. So those vertices that are not reachable from S, if there are any in the graph, will not be explored. But there's no harm in running the breadth first search algorithm again from another source to repeat the process, right? Please remember that. So you can explore all the vertices in the graph. Instead of getting one breadth first tree, you'll end up getting a breadth first forest, right? So now let's go ahead and discuss about how to use the pi attributes to be able to get the breadth first tree, right? So if you see in this example, what I have done is the blue lined arrows are the pi attributes, right? How do we use that to be able to output the tree? Right. So what do? I do this. Given a graph, G is equal to V, comma E with the source S, which is basically input to the breadth first search algorithm. I generate what is called a predecessor subgraph by using the pi attributes. So what are the vertices of the predecessor subgraph? The vertices of the predecessor subgraph are all the vertices of the given graph such that they are reachable from S. Once they are reachable from S, their pi attribute will be non-nil, right? will not be a nil thing, because BFS will reset it to the parent vertex, and then you take the source S. What are the set of the edges of the predecessor subgraph? It will be the vertex and its predecessor, right? Because that's how edges in the tree look like. So you can prove a theorem which says that such a predecessor subgraph is actually a tree, in the sense that it's connected and it has no cycles. So what breadth first search outputs is a tree or a forest of trees containing shortest path from the source to each reachable vertex. The edges of this tree are called tree edges. Here are the lemmas that we need to use to show the correctness of breadth first search, because the main focus of this course is not on algorithms. I have just stated the lemmas and not proved their correctness. Feel free to refer to a book like CLRS to check for correctness or proofs of all these lemmas. So initially you need a lemma which says that the shortest path distances increases as I explore the graph. So it says when you start from the source and then you reach a vertex u from the source, wherein delta of SU is known to me, and suppose u comma v is an edge in the graph, then what is the shortest path distance from S to v? It is at most the shortest path distance from S to u plus 1, right? Because I need to be able to consider the path to reach from S to U and then consider the edge UV. It can't be more than that. This is popularly called triangular inequality. The second lemma says that suppose you run BFS on a graph from a given source vertex, then when this algorithm terminates, for each vertex V, the value, the distance V dot D that the BFS algorithm computes will be at least the shortest path distance. Sorry, it will be at least the shortest path distance. It could be more. In fact, it will be equal to the shortest path distance for this kind of breadth first search algorithm, right? The third lemma says that as I go on exploring the graph, the shortest path distances increases, right? It monotonically increases. That's what the third lemma says. Fourth lemma says that the queue respects the order in which the queue strongly influences the order of exploring the vertices. For example, if you go back and see in this code, right in the beginning, when I look at the source X, S, right, it has two vertices in its adjacency list, R and W. I put W first and R next. And I told you at that time itself, there's no sanctity about it. I could have put R first and W next. I would have got a slightly different breadth first tree, but nonetheless, they would still be the shortest path distance from the source, right? That's what these lemmas say. It says that the queue respects the distance, enqueuing and dequeuing respects the distances of the vertices, right? So using these lemmas, I'll be able to show correctness of BFS. Correctness of BFS basically says that if I do BFS from a source, it will finish exploring every vertex that is reachable from the source, and it will output the shortest path distance in terms of the number of edges from that source to every other vertex. So this is all I had to tell you about BFS. In the next module, we'll look at depth first search, and also we'll look at algorithms for connected components in a graph. Thank you.